Okay, so we want to focus on this induction axiom. So this is the same, it's the same concept as what we looked at last year in Maths Fundamentals. We did a few examples of proof by induction. Okay, and there we met induction as a method of proof for proving certain facts. And that's, again, how we're going to look at it now. But we're seeing it here as the axiom, as I say, which differentiates the integers from the other number systems. So the fact here is that, as I kind of alluded to earlier, the positive integers, at least, the first positive integer is the integer 1. The next positive integer is 2, and that can be achieved by 1 plus 1. The next positive integer 3 is 1 plus 1 plus 1. And this operation of adding 1 each time, this is the key point, this will bring you through all of the positive integers. Okay? If you stop and think about it a bit, that isn't true of the rational numbers. So the rational numbers, remember, is all the fractions. If you take any rational number and any fixed kind of step amount, you can't generate all the rational numbers by just adding on that fixed step amount to the initial. Here we're taking an initial positive integer 1, and we're adding 1 on each time. But no matter what rational number we start with, and no matter what tiny incremental step we take, we'll always be skipping out rational numbers, if you like. Okay? So the rational numbers cannot be inductively built like this, using the operation of addition. Okay? And neither can the real numbers and so on. Okay? Okay, so this is what we want to really focus on today. Proofs by induction. So the way I want you to think is that the integers, what really separates the integers from all of the other number systems is this fact that you can do proofs by induction in the integers. Okay? You can establish facts about the integers using the technique of proof by induction, which isn't available to you to establish facts about the rational numbers and the real numbers in the same way, because you can't inductively kind of travel across all the rational numbers or all the real numbers. Okay. So we'll rephrase the axiom now into the more familiar kind of proof technique way that you met it in first year. Okay? And we got a bunch of examples to look at. So here we're looking at induction as a proof method. So we'll suppose that we've got some statement P of n, and we see many examples of these in the exercises. So P of n is a statement about the integer n. And the idea here is we want to construct a proof that P of n is true for all of the integers n. Well, the method of proof by induction, there's two key steps in it. The first is we make some, we prove some base case of the induction. Okay. So we prove, typically, if we're proving this for all positive integers, we typically prove that the statement P of 1 is true. And quite often that's a pretty straightforward proof. The second key step is proving what's called the inductive step. Then we want to prove that for every positive integer k, for all positive integers k, P of k implies pk plus 1. Remember, P of k is the statement about the integer k. So we want to prove the link that if the statement about the integer k is true, then the statement about the next integer, the integer k plus 1, must also be true. And if we can establish these two steps, the base case, which typically is P of 1, although it might start at some other integer, if we can establish the inductive step, the second bullet point there, what the induction axiom, or what the principle of induction tells us then, is we can then conclude, or what we will have done then is prove that the statement P is true of every, well, if we start at 1, is true of every positive integer, or if we start at some other initial case, it's true of every integer from that initial case on. Okay. So we'll begin by looking at this example, and this is something we proved last year. It's this nice addition formula. It's a nice formula for adding up the first n positive integers. Okay, so I'll switch to the overhead for this.
No, you say P1 is 2, is that just put n for 1?
Yes, yeah. We're looking at
Substituting n for 1.
substituting 1 for n. Yeah. So these are examples 1.2. So we'll do a few of these, and we'll do a few in the second lecture as well, and we'll look at any remaining ones in the tutorial next week. Maybe on some other days. So here, P of n is this statement. The sum from j equals 1 up to n of j is 1/2 n into n plus 1. Okay? So this is the statement about the integer n. May or may not be true, depending on what n is. We're going to prove it using induction. You can see the other examples after this, they get progressively kind of more complicated. Now, I should just mention that there's a very intuitive, very quick explanation of why this equation might be true. So, for instance, for n equals 8, what is this saying for n equals 8? It's saying 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. The question is, how do you add those? How do you add those up? Well, there's this interesting observation that if you add the first one and the last one, you add 1 plus 8, you get 9, of course. You add the second one and the second last one, 2 plus 7, you again get 9. Then you add 3 and 6, you again get 9. So if you pair them off that way, rather than going from the first, second, third, fourth, etc., you go the first and the last, and the second and the second. You see, they always add up to 9. Those pairs always add up to 9. And how many pairs are there? 4. There's 8 numbers there in total. There must be many pairs. Must be 8 over 2 pairs. Yeah. So 4 times 9. So this, if you like, is the n over 2 times the n plus 1. That you see in the equation. What's 4 times 9? 36. Now, more or less, that is a pretty strong argument that the thing is true in general. But we'll go through the induction method anyway, because it's a nice, simple enough example to see induction happening, and it displays all the important features of it, and it gives us a structure then we can use to attack more complicated statements. So the first thing is to look at the base case, which for us is going to be n equals 1. N equals 1, because if you look at the statement, I think these are all beginning of 1. Yeah, they're all beginning of 1. But the thing we're trying to prove is that for all integers n bigger than or equal to 1. So 1 is the first example. Yeah, that's the base case n equals 1. So what is the thing saying in the base case? Sorry, J. So what does this sum look like? When you add up all the integers j from 1 to 1, what are you adding up?
1.
Just 1, yeah. There's just a single term in that sum, so that's just 1. Yeah. All we have to do is just compare the value of the sum to the value of that formula. So when n is 1, is this question mark, is this equal to 1/2 times 1 times 1 plus 1? That's 1/2 times 2. Yeah, that is equal to 1. So yes, it is. Okay. So by observation, the base case is true. We just have to write out clearly what it's saying when n is equal to 1, and we just see it's true.
Well, the base case when P1 is true, that thing there.
Yeah, P1. Yeah, because P was the statement here where we had n. And here I've written it out with n equals 1, and we observe it's true. Okay. So we observe that P of 1 is true. Okay, now we want to go on to proving the inductive step. Okay, so now we want to prove, so I'll just stick in a box here the thing we want to prove, just to make it clear what's happening. So how do we prove this? Well, we would start off by letting k be some integer bigger than or equal to 1. And we're trying to prove an implication. We're trying to prove this implies that. The left-hand side implies the right-hand side. Now, the way to do that, using direct proof, is to assume that the left-hand side is true. We assume the left-hand side is true, and then by arguing carefully, okay, using the axioms of the integers, using mathematical manipulation, we attempt to derive the right-hand side. So starting off by assuming P of k is true, we attempt to deduce P of k plus 1 from it. Okay. If we can do that, then we'll prove the implication. Okay. But we must do so in a way that it applies to any k bigger than 1. Okay. So we assume P of k is true. What does that mean? In this specific problem, what does it mean to say P of k is true? Well, it means to say that the sum from j equals 1 up to k of j is indeed a half of k times k plus 1. Okay, that's P of k. Taken the original statement P of n, and I've just rewritten it with k in place of n. So this is what we're assuming. We don't have to prove this, we're making an assumption that this is true.
All you've done is replace n with k.
Yeah. Well, in terms of what I put down on the page, that's all I've done. But the key thing, what I've actually done in the course of the argument is that word. I'm assuming that's true. So I'm giving myself this result. And I'm allowed to work with it. I'm allowed to play with it. And what do I want to produce? I want to produce the following on result. I want to produce P of k plus 1. This is the inductive step, where we're exploiting this fact that the integers can be generated by induction. Well, what do you have to do to prove P of k plus 1? Well, we're going to have to tackle this sum, okay? Because that's the left-hand side, if you like, of P of k plus 1. Let's put a comment here. Now attempt P of k plus 1. So I say derive. So the key point here is from this. From this assumption I've just made. I've just made an assumption. And we want to use that assumption to prove P of k plus 1. Well, P of k plus 1 is an equation with this sum on the left-hand side, adding up all the integers j, and j equals 1 to k plus 1. 1 plus 2 plus 3 plus 4, etc., all the way up and finishing with k plus 1. And there's another important proof technique that everybody needs to know, and that's called filling in the gaps. I already know what I want to get on the right-hand side. If I want to prove P of k plus 1, I know what I need to finish up with.
Replacing n with k plus 1.
Exactly. Replace n with k plus 1 in the right-hand side of P of n. So what I want to get to is a half of k plus 1 times k plus 2. That's exactly. Yeah. If I can bridge this gap, if I can say that this is indeed equal to that, then I'll be done. That will be P of k plus 1.
How did you do it?
Well, that indeed is the question. How did you start it? You have to be careful because, of course, the thing that can go wrong is that you don't give yourself enough room. Of course, I'm an experienced professional at giving myself enough room. I hope. I'm always messing this up. Either I finish the thing up here and I've got a big gap, or else I end up having to move around it. Well, let's see if we can do this, right? So so that's the key question you're going to say. How do you get from here to here? How do you get started? So you're using the rules of mathematics, you're using mathematical manipulation, plus one other thing. That other thing is the assumption. We want to use the assumption. Now, the assumption is an equation, and it looks like quite a useful equation for this purposes, because it's an equation that takes you from a sum to a kind of formula involving k. And that's what we want to do overall as well, isn't it? We want to move from a sum involving k, or k plus 1, to a formula involving k. So it's a similar kind of thing. And indeed, these two sums look extremely similar, don't they? They just do. They almost look the same, except this one is a plus 1 at the top, and that one doesn't. So exploit that. The sum of the first k numbers plus the very last one. Okay? Yeah, I'm just playing around with this notation here. You're adding up all the j's from 1 to k plus 1. Well, you're adding them all up to k, and then you've got the final one. Okay? So I separate off the final j, if you like, the final k plus 1. Separate that off. Well, that's good, because what you leave behind then is exactly the left-hand side of p of k. It's exactly the left-hand side. Quite right, yeah. Exactly the left-hand side. So now I can use my assumption. I can simply replace this summation here by this one. Half of k times k plus 1. And I just need to justify that. So this is by the assumption I've made above. And this is good. I've got a formula involving k, and I want to get this formula involving k. So hopefully it's just a bit of algebraic manipulation. Is that right? Well, you see you've got k plus 1 as a common factor. So it's a half of k plus 1, all multiplied by k plus 1. That gets me towards it, because now look, I've got it written. It's not written as a sum anymore, it's written as a product. And k plus 1 is one of the factors. You just look at the other factor. You've got a half of k plus 1, but you can take the half out. It's a half into k plus, well, I want to leave 1 behind, so I better put a 2 there. So I'm going to multiply the 2 by a half, I get 1. And I've still got this factor of k plus 1. And you see that's complete. This is just a reordering of the factors. So we've achieved the step there. We made the assumption about p of k, and we were able to deduce this statement here in red, which is indeed. So this has derived p of k plus 1. So we can finish this off by saying then, by the principle of induction, p of n is true, well, for every integer n beyond the base case. From the base case on. Okay. Proof by induction is going to feature crucial stages in the number theory course, okay? Because induction is the thing that characterizes the integers. So at key stages, when we're proving all these other wonderful things about prime numbers and congruence and so on, at key stages, induction is going to be a major tool. Okay? So when I see you for a second lecture this week, I think it's on Friday, check the timetables. We'll look at some more of these examples and really get to grips with this proof by induction. But do be working on them in the meantime. Do sit down and attempt these problems in the meantime in this first batch.